Hey there! In this video, we are going to talk about how to solve exponential and logarithmic functions. Now, there's some useful properties that we're going to be using depending on the way the equation looks or is set up. So I'm going to go through each one of these with each type as we kind of categorize the different types of equations you're going to be expected to solve. But it's nice to kind of have these at the ready so you can figure out when to use each one as we go. So the first one is just using basic definition of a log. So going between the exponential form and the logarithmic form. The second one we call the like basis property, where basically if I have a to a power equal to a to another power, well, if the bases match, then the exponents have to be equal. So I can simplify the problem by just focusing on those exponents. And then the last property is a similar type of thing only for logs. We call it the one-to-one property of logs. If the log of x equals a log of y, well, then x has to equal y. If the bases match, then the argument's going to have to match as well in that situation. So the first type we're going to look at is what we call like bases. This is exponential equations. So you're going to see some exponents showing up in here where we can rewrite the two sides of the equation using the same base. Okay, I want it to look like this a to the x equals a to the y so that I can switch to x equals y in that case. So let's see an example of that. So here I have an equation 5 to the 3x equals 25 to the x plus 4. So what jumps out at me here is that I have just two expressions that are both exponentials. There's no like plus 5 at the end or anything like that that I have to deal with. It's just one exponential expression equals another. So that's one reason that I think like bases. The other one is that I have a base of 5 and then a base of 25, which is just 5 squared. So I'm going to use the like bases approach and rewrite that 25 as 5 squared. So now I have 5 to the 3x equals 5 squared to the x plus 4. And I can simplify the exponents on the right side there. It's a power to a power, so I'm multiplying. Make sure to distribute the 2 to both the x and the 4. And at this point, too, I have the same basis, so I can just drop out the bases completely. So the exponent 3x has to equal the exponent of 2 times x plus 4. It's the only way this equation can be solved. So from here, it's now just a nice linear equation. I can distribute the 2 and solve for x. So 3x equals 2x plus 8. And if I subtract 2x from both sides of that equation, I get x equals 8. And if you're ever unsure about how you've solved it, you can always plug this back into the original equation and make sure that it gives you a true state. Okay, the next property we want to use in an exponential equation is using logs. So that last property that I showed originally, if the log of x equals the log of y, then x equals y. That goes both ways. If I have two expressions that are equal, then I take the log of both sides. They will still be equal. And this can actually be helpful when dealing with exponents when I add in the power rule, as we'll see in this next example. Okay, so this one looks pretty similar to the last example we did. I have 7 to the x minus 5 equals 4 to the 6x. The big difference here is that I'm never going to get those bases to match. I can't rewrite 7 as something else to a power. 4, I can never get to be 7 to a power. So that like bases method is not going to work here, but logs will. What I'm going to do is I'm going to take the log of both sides of this equation. I'm choosing natural log, but you can do common log if you prefer. Natural log, one less letter to write, a little faster. We tend to favor natural log a lot of the times with these. Okay, so from here, now that I've taken the log, I've got the natural log of 7 to the x minus 5 equals ln of 4 to the 6x. I can use the power rule to bring those exponents out of the exponent position, and that is going to make it much easier to solve for x. So this becomes x minus 5 in parentheses times natural log 7 equals 6x times the natural log of 4. So I don't have the exponents there with variables in them anymore. Going to make it much easier to solve. It may be a little tricky to figure out where to go from here, but once you get the hang of this, it kind of goes the same every time. I'm going to distribute the natural log of 7 to get rid of the parentheses. So x ln 7 minus 5 ln 7 equals 6x ln 4. And you might notice I started saying ln because it's a lot of words. An abbreviation for natural log is ln. Okay, so now I have x's in two of my terms. I want to group those together on one side of the equation, and any term that does not have an x, I want to move to the other side. So I'm going to add the 5 natural log of 7 and subtract the 6x natural log of 4. Okay, and so I basically just swap those around. So now I have x natural log of 7 minus 6x natural log of 4 equals negative 5 natural log of 7. From here, now that I have those two terms on the left with an x in it, I can factor that x out. So it becomes x times ln 7 minus 6 ln 4 equals negative 5 ln 7. And believe it or not, I'm only one step away from my answer. I just divide out by what's in parentheses there to solve for x. So x is going to equal negative 5 natural log of 7 divided by natural log of 7 minus 6 natural log of 4. And if I needed an approximation, I could plug that into my calculator. This would be the exact answer there. So if the like basis method doesn't work, this is usually my fallback in that situation because it does take a bit more work. Okay, so next we want to look at some log equations and how I can use some properties to solve those. So the first one is using the exponential form. If I have a log equation, sometimes if I just swap it to the exponential form, suddenly it becomes much easier to solve. You want to only do this when you only have one log showing up in your equation. So either condense everything down to a single log and do this, or maybe you started out with that. So here's a nice example, very quick one of it. Log 8 of x equals 7.5. Well, if I could just convert that to its exponential form, I have x equals 8 to the 7.5. And well, that's something I can just plug into my calculator. And I get approximately 5,931,641.6. So it can be pretty quick if it starts out being that simple and the x happens to be in the right spot. Another option is to use a one-to-one property. So again, if log of x equals log of y, then x equals y. So this is great if you can take both sides of the equation and write them as a single log with the same base. For instance, here, got a lot more logs than we were dealing with in the last one, and there's x's showing up in multiple logs. I've got log base 19 of 4 plus log 19 of x equals log 19 of x minus 3. And so that converting to exponential, not really an option here because there's just too much stuff going on. But I can condense the logs. So on the left, I have the two logs adding. I can rewrite that using the product rule as log 19 of 4x. And now I have just one log equals another log, and their bases match. So I can just drop the logs out completely and just say, well, 4x has to equal x minus 3 in this case. And then subtract x from both sides of the equation. So 3x equals negative 3. And then divide by 3 to get x equals negative 1. Now, there is one thing you have to be really careful with when you're solving log equations. We always have to remember that we cannot take the log of a negative number. So when you get to the final answer, you want to make sure that that answer does not cause you to get a negative inside of a log when you plug in the x and simplify. And with this one, if I see I have that log 19 of x, if I plug in negative 1 there, not going to work. So it turns out that even this solution that I came up with does not actually work in the original equation, which tells me that there is no solution to this one because that's the only one I found by solving it. So this one happens to have no solution. So make sure to always check your answer, particularly if it's negative, but it's a good idea to check every time when you're solving a log equation. And that is it for solving logs and exponential equations.